Okay, so this actually turns out to be not okay, so constant of proportionality is actually square root of 2 over t sub. So this is incorrect. This is incorrect. And did anybody get a chance to verify that these two signal vectors are orthogonal to each other? Okay, fine. So we will move along. If you didn't do it yourself, maybe today in the class we will go over the math. Okay, so we went over all these different several modulation schemes. We went over the derivation of the symbol error probabilities and specifically the union bound and improved union bound that some of you had suggested last time. Then we quickly saw this description of the relationship between the symbol energy, the symbol rate and the bit rate. How to relate bit rate, information bit rate to the symbol rate, the rate at which the symbols gets transmitted when we have a certain coding rate and when we are using certain modulation scheme. So there is some easy formula that is useful to remember. And then we saw that the actual real life communication system has this additional part apart from this digital domain blocks that we have been studying. And one key component is this frequency up conversion, down conversion. And that is the topic of our discussion today. And we saw that this frequency up conversion and down conversion has multiple reasons, that it is required for multiple reasons. In fact, when the communication era started, way back in maybe late 18th century, when Marconi demonstrated the long distance communication, I think there was a transatlantic call that was made from England to America. There, the main achievement was actually the use of electromagnetic waves for transmitting the information signal over such a long distance, over the entire length of Atlantic Ocean. And so in the early days, all of these advanced concepts of signal processing that we have looked at, the channel coding or the source coding, those were not there. The early communication systems were very simple. They were just analog modulation. And we will probably briefly look at the analog modulation in this course. But that time, the main engineering achievement was to build a radio which can transmit messages over long distances. And people realized in those early days, and now there is a good mathematical theory behind it, which says that, first of all, you need electromagnetic waves because they propagate well in the atmosphere. And that is kind of well known. The light propagates so well in the atmosphere, the light is nothing but an electromagnetic signal. So that was the first realization. And the second realization was that the antenna can help how far the signal goes. If you think of light as being emanated from your household bulbs, then the filament of that bulb can be thought of as an antenna. It is radiating the electromagnetic energy, electromagnetic signal, which is the visible part of EM spectrum that I think you would have studied in your physics courses earlier. If you want the light to propagate further, then you need a better antenna. And one type of better antenna is your torchlight. If you're walking out in a dark night and if you have the torchlight with you, you would know that the bulb is kind of at this focal point of a parabolic reflector. And that parabolic reflector is sort of an antenna which kind of transmits that EM energy in a well-defined direction, and therefore it propagates farther on, and it is stronger. The light beam is stronger compared to what would come out of a regular bulb. And if you are really intent on illuminating this dark area when you're going out in the night, then you will carry with you a bigger torch, which will have essentially a bigger reflector. And so the bigger the antenna, the farther the EM wave propagates, and it is stronger as well. It turns out, and we are not going to go over the math of that, is that if you reduce the frequency of that EM wave, then the size of the antenna required for the same strength of the EM wave to be realized at a certain distance becomes bigger. And just roughly speaking, if you simply take the BPSK signal that we have studied, or QPSK, or Emery PSK, or Emery QAM, and if you just convert them into voltages, then we'll see very shortly that the corresponding signal has a frequency spectrum which is centered around 0 Hertz. It still has some frequencies. It's not that it's just constant DC signal, obviously not, because you are going back and forth across different symbols, and so you are changing something. And whenever you are changing the signal, it cannot be a constant DC signal. So it is not a single frequency DC signal with exactly 0 Hertz of frequency. It has certain spectral band, but that spectral band is centered around 0 Hertz. We'll shortly see a visual depiction of that. The problem is that if you want to transmit such a signal which is centered at 0 Hertz to a sufficiently long distance, let's say maybe 1 kilometer, then you would need an antenna which is the size of a football field, which is clearly impractical. I mean, today you don't see phones having antennas which are anywhere close to that size. In fact, today's communication devices have antennas which are so small that you wouldn't even know where they are located. So one of the main reasons for using the sinusoidal waveform for modulating design is that it allows the signal to travel over large distances with antennas which are small in size. And then the other reason, which is something we are going to look at also today, is that it allows the placement of the transmitted signal spectrum, I should say here, placement of the spectrum, the frequency spectrum, of the transmitted signal at some desired location. You can take this modulated symbol spectrum and you can slide it in a very nice manner. And that allows what is known as frequency division multiplexing, FDM, arrangement of signals from different users. So these are some of the reasons why the sinusoidal waveforms, the electromagnetic waveforms are the preferred choices for modulation. Now, it doesn't have to be sinusoidal waveform. If you think of it purely from mathematics, we saw that those functions G1 of time t and G2, again a function of time variable t, they can be some other functions. We saw examples of some rectangularly shaped functions, which also satisfy those two requirements. And so they don't have to be sinusoidal waveforms for the modulation principle to work. But today, typically, it is the EM waves which are used in the practical designs. And with that, we saw last time that there are three actual different notations of the modulated signal, and specifically the frequency up conversion and down conversion that we can utilize. And so I kind of elaborated upon this slide a little bit more. And so let us directly go to that detailed version of the slide, which is what I have written over here. So the first notation of the transmitted signal is called the quadrature notation, where a particular constellation symbol, remember it as, if you are considering two-dimensional constellations like UPSK or M-Array PSK or M-Array Quam, then each of these symbol points can be specified by just two coordinates. The in-phase coordinate, which we have denoted as S of I, and quadrature coordinate, which we have denoted as S of Q. So that S of I and S of Q together, they make up what is known as the complex symbol, or the complex envelope of the symbol. And it is this signal which is actually truly the information bearing signal, which I said is centered around 0 Hertz. And then the rest of the terms in this equation here, cosine and sine, their purpose is to move that frequency spectrum to what is known as this carrier frequency, FC. So here, compared to the previous slide, I have written the math in a little more careful manner, where I have included the square root of 2 sim multiplier. And this we saw at the beginning of the lecture today that this is needed so that now I can write this S of t as nothing but Si times Gi of t and Sq times Gq of t. Gi is this signal here. Gq is this electromagnetic wave. And Gi and Gq satisfy those two properties. They are unit energy and they are orthogonal to each other, meaning as vectors, they are perpendicular. Okay, so this is the quadrature notation. You think of this Gi as forming the x-axis of that IQ plane. So this is x-axis, and this GQ as forming the y-axis of the IQ. Now, it is an easy math for you to show that if you take this complex number product and take just the real part of it, you get this expression. So this is the what is known as the complex envelope notation. Here we are remaining in the complex number domain. The actual physical signal that gets transmitted cannot be complex valued, and so we have to take the real part. But otherwise, everything inside the bracket is purely complex. And then the third equivalent representation is the polar representation, where we represent the same signal S of t as possessing certain magnitude, which is, it turns out that it is the magnitude of this complex valued symbol, and also possessing certain phase, which also is the phase of this complex number. And the transmitted signal is just the cosine of this carrier frequency with this phase and this amplitude. And okay, one thing I forgot to write here is that this also gets multiplied by square root of 2 times 2 divided by symbol ratio. So this is these are the three equivalent representations of the transmitted modulated symbol. Okay. Now, in order for us to appreciate this frequency up conversion and down conversion, I wanted to postpone this as much as possible, but I can't do it anymore. We have to at least get a definition of Fourier transform. So you see, this is probably I think after this, we probably will have about 2 more weeks, about 4 to 5 more lectures remaining in the semester. My purpose in this remaining few lectures is to introduce you to the Fourier transform. I don't know how much progress we will make there, but we will see. We'll find out as we go along. But before we get into more detailed look at the Fourier transform, I wanted to just give you the definition of what it is. Okay, so the Fourier transform has this definition. You take a time domain signal, S of t, and you perform this integral to get the Fourier transform S of f. And it's a lot like the Laplace transform that you may have studied in your first semester. Laplace also does this type of integral, except for Fourier transform, the integral is obtained by multiplying S of t with this complex exponential of negative j to pi f t. Now, if suppose we say that the resulting Fourier transform, this is called also the spectrum or the frequency spectrum, or sometimes just the spectrum. If we assume that the frequency spectrum, the frequency content that we get by taking Fourier transform is non-zero only over certain range of frequencies, let's say f low to f high, then we can get the original signal back, the time domain signal back, by performing what is known as the inverse Fourier transform. So here we are given S of f, and then we multiply it by this exponential, and then we integrate it over f low to f high. This is sometimes called the synthesis operation. Synthesis. And this is sometimes called the analysis operation. Okay. Now, before we get into the detail of what this Fourier transform is, let me tell you the way to think about this possibly is again to consider the example of something that we all are very familiar with, the light which is visible. So you all would have dabbled with some or other form of painting. And in that, maybe you will have some a box with different colors of the paints. And sometimes you would want to mix and match. So maybe you will take your paintbrush and use it to get a little bit of the green. And then you put that green maybe on a dish or something. Then you take a little bit of red. And then maybe you take some amount of blue. And all of those colors you mix in this dish. And then you want to see what comes out. Now the color that will come out will depend on the proportions of the green and the red and the blue that you would have used. If you use very large amount of green and little bit of red and blue, then the color that comes out will look a lot like green. Instead of that, if you use a lot of blue, maybe a little bit of red and very little green, then maybe something like purple will come out. So what you are doing that time is you're taking different colors, which we can think of as different frequencies, and the amount that you take of those colors is specified by this S of F. In our case, we are considering only 3 frequencies. Let's say the lowest frequency is some one color. Maybe we are having one medium frequency and one high frequency. So there are maybe only 3 frequencies. So this integral becomes just the summation over those 3 frequencies. And let us say in this example, we took the blue, the most, little bit of red, and the smallest of green. Then S of F for F equal to blue will be the highest. S of F for when F, the frequency is the frequency of the red color, will be medium. And then S of F for F equal to green color will be very small, maybe negligible. So S of F specifies kind of the amount which you are mixing. This part here is nothing but the electromagnetic wave itself at that particular frequency. It is what is oscillating, what the color light that gets emanated from that color. So the term together, S of F times this exponential of j2 pi ft, you can think of it as the actual color signal that reaches your eye. And then this integral, or for our case, we replace it by just a summation over 3 colors, is the mixing that happens in your eye. Your eye gets these 3 different colors. The intensity of those colors you have specified by choosing this S of F carefully. And the corresponding EM wave that comes out of that portion of the color blob that you would have put in the dish, that signal is given by this S of F times this EXP function. And the summation actually happens within your visual system. And therefore, the color that you see, this S of T that you see, is purple. And then you say that I have synthesized purple color. Synthesis, the English word synthesis means making something. You take multiple things, you kind of merge them together, and you have synthesized something else. In chemistry, synthesis is very common. You take different chemical compounds and you mix and match them, and then you get something which is a synthesis of those original compounds. So think of inverse Fourier transform as synthesizing your actual signal, in this case purple, using some ingredients that you are specifying with different intensities. Now, suppose that you have the color purple with you. Suppose somebody is giving you this particular waveform, which to your eye looks like purplish in color. That is all that you have now. Okay, now you are in a different room. Now you are not actually composing this new color, but you are in a room where you're just looking at that color. And the question is now different. You want to know, maybe your friend who is actually drawing this painting, what composition of red, blue, and green he or she has used. That is now the question. And so you take this purple color, this S of t, and you analyze it now. Now you are a chemist which is using sort of a microscope to see what this bloody thing, or in this case, the purplish thing, is made up of. And now you take this S of t, you put it under microscope, meaning that you do this multiplication with frequencies of different colors. And what will come out actually, surprisingly, through this integration is the intensity of the individual colors. When this frequency F becomes the frequency of red, it will show that red was used with medium intensity. F becomes frequency of the blue color. S of F will be higher, which means that in purple, blue is little stronger. And then when F becomes the frequency of green, it will become tiny amount. And for all other frequencies, S of F will be 0. And so now you know that this is how you can make this particular purplish looking color. And by doing that, you have kind of obtained the frequency spectrum of the purple color. Spectrum has 3 frequencies corresponding to red, blue, and green. And the way you did it by analyzing this S of t. So analysis and synthesis, these are 2 kind of complementary operations. I will give you even more concrete example. When you pass white light, a ray of white light through a prism, and then you see the rainbow colors coming out of the prism, you can think of the prism as doing the analysis. Basically, it tells you that this white light is made up of all of these different frequencies. It kind of separates out each frequency and tells you the amount present of this particular frequency in the white light. So the prism can be thought of as doing some type of Fourier transformation of this ray of white light. It is analyzing what frequencies it is made up. Now you know from your physics course that if you put next to this prism another prism just vertically flipped, then it will take all of these different colors of light as the incoming rays, and then it will merge them. It will do this summation or integration, and what will come out is the white light itself. So now you are synthesizing white light by means of this other upside down prism. And so that prism is doing inverse Fourier transform. So You see, I have said this at the beginning of the semester that a lot of the topics that we do in this course end up being very close to us, meaning it is something that we do all the time without realizing it. When you are looking at a picture or maybe even this slide and you see the outer border being green and maybe one uh, border below in light blue and other letters being in black, your brain is already doing what? Is it doing Fourier transform or inverse Fourier transform?
Synthesizing.
For you to know that this is green in color, this is light blue in color, this is black in color, your visual apparatus and then ultimately the brain is doing what?
Transport.
Synthesis, it will mix colors and show
Speak
us
louder,
different.
I can barely hear you.
Synthesis, it will mix different colors
I
to
can't
show us
hear you.
new
Your
colors.
voice is too faint.
Synthesis, it will mix different rays of colors to show us new colors. The color of the
Your voice is very weak, or maybe let me see, my volume is... Okay, can
It
you...
might be doing inverse Fourier transform.
Might inverse Fourier transform.
Because I think because brain accepts white light and then what we see is converted. Means we see different colors like green and blue here. So might be it is transforming it to different color. And synthesizing the
Yeah, I mean, okay, we can look at it in a slightly different manner, the way you are saying. But the way I like to think of it is that my brain is just getting some electromagnetic waveform, which is this S of t, just getting some time domain signal. And then from that, it is figuring out that in this signal, green is present, blue is present, black is present. So it is kind of analyzing that signal. So in some sense, I would say it is doing the Fourier transform. I mean, the other example is your hearing system, right? Your ears. When I speak, my voice will look different to you compared to somebody else's voice. Or more simply, a male voice sounds different from a female voice. And the reason is because the female voice is known to have this S of F. Remember, this we are calling to be the weighting terms. How much of a particular frequency gets emphasized in the signal S of t is determined by S of F. So for female voice, this S of F is pretty low at low values of F. But as you make F a little larger, then S of F becomes stronger. Whereas in the male voice, it is the opposite. S of F is stronger for the low frequency waves. And as you make frequency larger, this S of F becomes smaller, meaning that male voice is mainly made up of, male voice is synthesized by our auditory system, the vocal cords and these, what we call swarpeti in our throat. That is kind of doing the synthesis. It is taking different frequencies that our lungs generate, and it is mixing them in a specific manner, where in the males, that mixing happens whereby the lower frequencies are emphasized more and the higher frequencies are kind of attenuated. And so you hear the male voice at a lower pitch. Female voice, on the other hand, in the synthesis operation, this S of F is stronger for higher frequencies. So again, this part of our body is doing the synthesis. And then this part here, ears, are doing the analysis. They listen to some signal, audio signal, and they make out whether it is made up of low frequencies or high frequencies. Right? So, our auditory system inside our body and brain is also continuously doing the Fourier transform. So that is why this is also a very interesting topic. If you just look at the math of this Fourier transform, these two equations that I have put here, they may seem meaningless to you. You may feel kind of even intimidated by it. You may feel that I don't know what these equations are. But they are actually extremely familiar to you. You do it all the time. It's just that you need to develop awareness that this is what you are doing. This is what your brain is doing. And once you become aware of it, then this entire topic of Fourier transform becomes very nice, beautiful topic. That I mean, something that you discover the engineering design of yourself, so to speak. You know, someone has said that there are engineering problems which are puzzles and engineering problems which are mysteries. And so the question that came up was, well, what is the difference between puzzle and mystery? And so this fellow said that puzzle is an engineering problem that is not solved, but we think we can solve it. Maybe the design of some really very fast bullet train. I mean, maybe nobody has made a bullet train that goes at, I don't know, speed of an aeroplane. So it's an engineering problem, but maybe it is solvable because all that you need to do is take today's bullet train technology and maybe, you know, make it really very fancy. I don't know. I'm just making up. I'm not a mechanical engineer. But so that would be classified as a puzzle. A mystery is something that we don't know whether we will ever get to the answer to. And so the way our mind works, the way our brain works, some people think that it is a mystery. Today, maybe some little enthusiastic, ambitious people are saying that it is not a mystery anymore, it is a puzzle. It's a personal opinion, but maybe those who are thinking of the operation of brains, our brain, as something of a solvable problem, maybe they are getting some hint from this type of equations that a lot of what our brain does is not only that Bayesian mathematics that we have seen earlier, but it is also this type of analysis and synthesis. Okay, so I will move now faster. So I'm going to go over two theorems. I'm not going to go over the proofs of this theorem. Today, you just accept these theorems. Okay, they are theorems of Fourier transformation. You just accept them. Maybe later on, if we do have time in the semester, we will prove this theorem when we actually do a more detailed study of Fourier transform. But today, you just accept the statement of this theorem that the one theorem is called the Modulation Theorem, which says that if you take certain signal S of t, and then you multiply by exponential oscillating at some frequency fc. This is, remember, our carrier frequency. Then that product S of t times this exponent of j2 pi fct. If you look at its Fourier transform, it is the same Fourier transform as S of f, except it got slided or it got shifted, it got moved by fc hertz. This is a very powerful theorem. Okay, I hope you understand the meaning of it. If you don't, then just wait. On the next slide, hopefully it will become clear. Then the second theorem is called the Symmetry Theorem. Okay, and what it says is that if, see, remember, I didn't say anything about what S of t is and what S of f is. Its definition doesn't say it. You can put a real signal as S of t, or you can actually have complex valued signal as S of t. So this theorem says that in case if this signal S of t is real valued, and our speech signal is always real valued, light that we see is always real valued. Most of the signals are real valued, but in our engineering design, we can come up with complex valued signal. For example, our complex envelope representation over here, this is complex valued signal. This is not real valued. So in case if S of t is real value, then its spectrum, the Fourier transform, has a specific characteristic to it. That first of all, positive and negative frequencies both are present. Secondly, if you take this S of f at certain frequency f, it turns out that it is same as the value of the spectrum at the negative of that frequency. Except maybe you have to do this complex conjugation if this S of f is complex. If it is not complex, then this complex conjugation has no meaning. And so this is sometimes called the mirror symmetry. Means the spectrum, the way it looks on the positive side, it looks same on the negative side. It's like you are standing in front of a mirror and you get an image on the other side. So these are the two important theorems. And this is what we are going to now make use of. So what I'm going to do now is I'm going to take this modulating signal Si plus Js of Q, which is this complex modulating signal, maybe 8 array PSK or 32 array QAM, anything. And I'm going to take a lot of symbols. Okay, I'm not taking only one symbol now. I'm taking maybe 100 symbols or 1,000 symbols in a sequence. And that is a kind of, obviously, the time domain sequence. Symbols are occurring one after another in time domain. So I'm going to call it some signal S of t. And I will take Fourier transform of it. I'm just going to pass it through this analysis equation. And it turns out that, as I said, it will have some frequency content. This is, by the way, showing what that complex envelope of the modulating signal looks like in the frequency domain. What different frequencies are present. And so this now here would be Fi, and this would be F low. Maybe F low is negative. Forget about this pulse shaping. Okay, in order to be exact, I have to use this terminology which we haven't defined yet. So no, don't worry about it.
Sir,
Yes.
sir, how can the frequency negative?
How can the frequencies be negative? Okay. I can always do negative sign inside this complex exponential, right?
Yes, sir.
Nothing prevents me to do that. Now, if I
Yes.
call the frequency as the multiplier of j 2 pi t, whichever it is, I just define the frequency like that. Then for this complex exponential, I get f. But for this complex exponential, I get minus f. So if this f is positive, this has to be negative of f.
But what does negative frequency represent then?
Right now, let's not get into the physical meaning of it. But
Okay.
mathematically, you understand, right? That I can
Yes, sir.
mathematically define negative frequency, just like by putting a minus sign inside the bracket of exponent.
Yes, sir.
Okay, so that is what we mean when we say this f loop can be negative.
Okay, sir.
Okay, so this is the spectrum of the complex envelope. And you see, I purposefully made it asymmetric. This is not symmetric. So this part is slanted, this part is vertical. So even if I suppose that, let's say f low, which is a negative frequency as we said, even if f low is negative of f high, then you can see that there is no mirror image symmetry. This spectrum cannot be kind of flipped horizontally and it will look the same. The reason is because this is complex value. Okay, now the next thing we are going to do is multiply s by this exponential signal. So we are going to look at the spectrum of this whole thing inside the bracket. And that is where we are going to use the Modulation Theorem. What we are doing is we are multiplying s of t with this exponent j to pi f ct. And we said that according to this theorem, all that happens is this s of f. If we think of it as some type of strange looking box, we just lift it from where it was and we move it by f of c hertz. And so that is what happens. Because of the modulation theorem, this signal, which was inside the curly bracket, has the same spectrum as the original signal, except it came to f of c. Here it was at 0 hertz. It was centered at 0. Now it got centered at f of c. Nothing else changed. The width of the spectrum, let's say this b is f low, f high minus f low. That remained the same. This is sometimes called the bandwidth. But not only that, the bandwidth remained the same, the content of the spectrum remained the same. If we take a box and we move it from one position to the other, nothing inside the box changes. So that is what is happening. We are just moving the spectrum by multiplying with this exponential function. And then the last thing that happens is we take the real part, right? In the complex envelope representation, we take the real part of this to get our actual transmitted signal. And from that symmetry theorem, as soon as we take the real part, we get the mirror image symmetry. So the spectrum that was here at f of c, its copy pops up at negative of f of c. It's a copy, but it's a mirror image copy. So this slanted line is this slanted line. And this vertical line is like here. And more specifically, I can say that this is fc plus f high. Then that frequency will become negative of fc plus f high. And so this is the reason why this is called frequency up conversion. We take this signal, and which is centered at 0 hertz. By the way, this is also sometimes called the baseband signal. It is the basic band, the band which is at 0 Hz. It's the base of the frequency spectrum. And this is called the radio frequency band, the RF or radio frequency band. So this frequency up conversion, down conversion allowed us to move the baseband to the RF band. That is why it is called up conversion. We are up converting the band. So in summary, the frequency up conversion moves the Fourier transform of the modulated symbols to an RF band. And therefore, you can imagine that the down conversion will move it back to the baseband. Okay. So that diagram I have not shown here, but it is kind of the inverse of this diagram. You go kind of upward in this slide. Instead of going from 1 to 3, you go from 3 to 1. So you get something which is the bottom picture, and from that you get the top picture, which is called the frequency down conversion. From f of c hertz, you come back to the baseband. And again, this is needed because the baseband signal doesn't travel much, but the RF signal travels a lot. Alternatively, you need a smaller size antenna for the communication to occur. And then the other aspect of it, which you can probably now imagine, is that it allows us to do the channelization in frequency domain. You see, today when you turn on your FM radio and you go from 88.5 to maybe 90.1, those are different channels. And actually FM radio has maybe, I don't know, 100 such channels. You have to kind of keep on tuning your radio to different frequencies, and it will give you different stations, different audio channels. That entire signal is coming to you together. It's kind of frequency division multiplexed. All those different signals are arriving at the radio antenna collectively. And then the radio, when you tune it to a particular band, it kind of extracts out only the audio signal corresponding to that particular band. It is the modulation which is allowing the FM transmitter to do that, right? Because FM transmitter will take some channel, some audio station, and it will put it at FC1. Then for another station, it will put it at FC2. Maybe this is 88.5 megahertz FM radio. Maybe this is, I don't know, 88.9 megahertz FM radio station. Maybe this is 90.1 megahertz. So as you tune your FM radio, you are going from here to here to here. And then sometimes there is nothing there. And so you just hear the noise. But then when your radio tunes to a valid station, it sees this particular spectrum, and that is the audio you start hearing. This entire scheme is not possible if you don't do modulation, because in absence of modulation, all of this TX1, TX2, TX3 will be sitting at the baseband. And if the spectrum are kind of on top of each other, you can't separate them anymore, the way you are able to separate it in this way. So this is another reason why modulation is required in today's systems. Okay, so now we will go over something that we have kind of already done to a large extent. So we are kind of going over maybe a detailed version of it, okay? Which is, what is this frequency up conversion, down conversion? And the reason I want to focus on it is because this is going to be a very nice application of the linear algebra that you have studied in your math, high school math. Okay. So what I'm going to ask you to consider is a simple matrix. I'm calling it G mode. And it is made up of only two vectors, G1 and G2. Right? So the matrix looks like this. And as you may have imagined, I'm going to require that each of these column vectors of G mode, G1 and G2, they have unit length, meaning if I take dot product of G1 with itself or G2 with itself, I get 1. You know from your earlier math studies that if you take dot product of a vector with itself, you are measuring the squared length of that vector. And then the other requirement is that the two column vectors are perpendicular, meaning if you take dot product of one with the other, you get a 0. Meaning that they are 90 degrees oriented with respect to each other on certain dimensional surface. So this is the question that I ask you. If I do this matrix product, G mode transpose with G mode, what do I get? So this is something that I will ask you to think about while I take a very quick.
Yes, sir.
Identity
Sir,
matrix.
identity matrix.
Yeah, it's going to be a 2 cross 2 identity matrix. Good. Because what happens is in this matrix product, on the diagonal you get the vector multiplied with itself, which is 1. On the cross diagonal you get vector multiplied with the other vector, which is 0. Okay. So by the way, what this tells you is that G mode has a very nice inverse. The inverse of G mode is nothing but the transpose of itself. Okay. So I can even say that therefore G mode inverse is nothing but transposing that matrix. Typically, the inverse of a matrix is a very cumbersome operation, except if the matrix is orthogonal. Then it is just very easy. You just transpose it and you suddenly get its inverse. So coming back to our simplified model, remember we have constellation points. We have so far considered only 2D constellations. So there are some M points in a two-dimensional plane. And M can vary. It can be 2, 4, 8, 16, any power of 2. And that power, we are calling it to be small k. And then because there are a total of M points, if I pick mth point, mth symbol, then it will have two coordinates, SM1 and SM2. These are simply the coordinates of this point. The way we would think of the frequency up conversion that we just now saw, it is that it takes this S of M and it multiplies that S of M with G mode. And G mode is made up of these two signals, G1 and G2, which are unit energy and orthogonal. And when I do this matrix multiply, I can write it as G mode as just G1 and G2. And then S of M is S of M1, S of M2. And so what this matrix multiply does is it actually takes this vector, weights it by SM1, takes this vector, weights it by SM2, and you suddenly get this signal, which is the transmitted modulated signal. So components of this S of M, SM1 and SM2, are kind of, we are using it to weight G1 and G2. And then you add the weighted combination. So the technical term is called the linear superposition of the column vectors of this matrix G. Can anybody tell me what would be the other way to say this based on what we just now discussed? What am I doing here when I do something like this?
Matrix multiplication.
No. I'm asking you in terms of that Fourier transformation discussion that I did. I used some specific terminology there. And I'm asking you to connect that terminology with this.
Frequency of
Synthesis.
Right. So this operation is a lot like a synthesis operation. Right? I'm synthesizing my transmitted signal. The way I do it is as if I pick two colors, G1 and G2, I mix them up in different proportions. The proportions are specified by this vector Sm, the elements of the vector Sm. So linear superposition, but also synthesis. And then in the absence of noise, so now this is the transmitted signal, and in the absence of noise, you get the same signal at the receiver. So received vector R is G mod Sm. And so what the receiver does, or the frequency down converter, what it does is it multiplies R with G mod transpose. And so G mod transpose R is G mod transpose times G mod times S of M. But we saw on the previous slide that this product is identity matrix. And so I simply get S of M back. I down converted to get the original signal back. And this G mod transpose can also be written as the dot product or the inner product of G1 with R and G2 with R. And so what would you say this? What is the receiver doing here? It is getting some signal R, and from that, it is basically determining this weighting coefficients. What are this SM1 and SM2 by doing this operation? So this would be analysis. So synthesis and analysis, these are general terms. The Fourier transformer and Fourier inverse transformer does that, but here even frequency up conversion and down conversion can also be thought of in terms of that. So when we meet next time, we are going to go over the same thing in a little detailed manner we'll draw actual block diagrams of what these operations are at the transmitter, what these are at the receiver. And you see here, I just have restricted myself to two-dimensional schemes. The vector S of M is just 2 × 1 vector, which is, by the way, all the schemes that we have seen. And it covers a lot of the schemes, okay? In fact, I would say that most of the popular schemes are just 2D. Your phone today is most likely using either QAM or PSK, which is 2D scheme. So not to say that these 2D schemes are not representative. In fact, they are the most representative of all schemes. But with this math and with this particular viewpoint, we don't need to restrict to two-dimensional space. The linear algebra can be extended to k-dimensional space. Basically, there are k different perpendicular axes or dimensions. So that is one thing we will do when we draw these block diagrams. And remember here, I literally took this G1 and G2 as vectors. In reality, these are actually electromagnetic signals which happen over time. And so we are going to now also start looking at the time variable t when we meet next time. So I'm going to stop over here.